Hello, everyone. Welcome to pre-lecture number 2. And this we're going to review a little bit and expand upon intermolecular forces. And if you would like some more information on this, feel free to check out your textbook, Chemistry 2.0 by Flowers. We're in chapter 10, sections 1 and 2. Okay. So in class on Tuesday, we went over different types of intermolecular forces, also called van der Waals forces. So the weakest of those is dispersion forces. Then we have dipole-dipole interactions, then hydrogen bonds. And of those three interactions, they all have some sort of partial positive or partial negative charge holding them together. And then for this last section, we have ion dipole and ion-ion forces, where we have, anytime we have an ion, we have a full positive or full negative charge, and that will hold the ion and the dipole or the ion and other ion together, and they are our strongest intermolecular forces. Okay. So in this pre-lecture, we're going to dig a little bit more into what each of these looks like. So we'll start with dispersion forces, occasionally called London dispersion forces. These are going to be present in all states of matter. So no matter what it is, dispersion force will be present. And what causes these are electron movement within our atoms or our molecules. The electrons are in constant motion, and so at any point in time, the electrons may be unevenly distributed, creating an instantaneous dipole, where electrons are maybe more on one side of the molecule than the other, creating a partial, very small partial negative charge, and the other side of the molecule would then be partially positive. Okay. These tend to be characteristic in, or tend to show up more in larger and heavier molecules, because the larger the molecule is, the more electrons it will have, and the greater the dispersion forces will also be present. Okay. Something to remember with dispersion forces is that if an atom or a molecule has a very large electron cloud or has very large mass, it's said to be very polarizable, meaning that it will have large dispersion forces, again, because our electrons can end up on one side or another of the molecule and create that instantaneous dipole. Okay. So what sorts of molecules tend to have dispersion forces? Do we identify them? So characteristics of elements or molecules that have dispersion forces is they could be a single element. So even when it's a molecule of a single element, like our halogen series here, F2, Cl2, Br2, I2, At2, all of those are a single element, but they're dominated by dispersion forces. Another thing is molecules that contain bonds that are non-polar. So that relates to the electronegativity of the atoms. The classic example there is hydrocarbons. So anytime we have just carbon and hydrogen, we would say that that molecule is dominated by dispersion forces because it is non-polar bonds. Okay. We could also think of a molecule that has polar bonds, but are all symmetrical. So an example of that is CCl4, where the carbon chlorine bond is going to be polar, but all of those polarities cancel out to 0 because they go in equal and opposite directions. Okay. All right. That transitions us then into our second strongest intermolecular force, dipole-dipole interactions. And so in a dipole-dipole interaction, you have some sort of molecule that has a partial positive charge on one side and a partial negative on the other. We designate that with lowercase delta. So this is the Greek letter delta. And so the partial positive, we would put delta plus, partial negative is delta minus. Okay. And when we have that separation of charge, we call that a dipole. And so the polarities of the molecules are going to be determined by the electronegativities of the atoms bonded together, as well as the geometry of the molecule. And so we're going to practice this more in class on Thursday. But the key thing to remember is that if a molecule is totally symmetrical, the individual bond dipoles will cancel out. And overall, our molecule may not be polar. So if you think back to that CCl4 example on the previous slide. Okay. And so an example of this, if we compare HCl and F2, they have the same number of atoms, they have approximately the same molar mass. However, if we were to lower the temperature of a reaction vessel that contained both of these at 150 Kelvin, the dipole-dipole interactions between HCl would be sufficient enough to cause them to stick together, because we would get attraction between that partial negative and partial positive, and it would actually turn from a gas to a liquid. F2, because it only has dipole-dipole forces, is going to remain a gas though, and that is because it has a lesser amount of intermolecular forces, okay? And so this is our medium strength intermolecular force, which can be a little tricky to identify, but here are some common trends. So anything that has dipole-dipole interactions must have multiple elements. Within those multiple elements, the bonds that they form must be polar, and so they need to have an electronegativity difference. Again, we'll practice that a little bit more in class on Thursday. The other thing they'll need is bonds distributed in a non-symmetrical fashion. So compared to CCl4, what if we have CHCl3? In that case, we no longer have a totally symmetrical molecule, and so we would end up with a dipole-dipole interaction there, okay? Right, next up we have hydrogen bonding, and really hydrogen bonding is an extreme form of a dipole-dipole interaction, but it's so extreme that we identify it as its own thing. And so a hydrogen bond will occur when a hydrogen is bound to one of the three most electronegative atoms, which are nitrogen, oxygen, and fluorine. I always remember it as the NOF monster, NOF, but I've also heard it as FON, FON, monster, whatever you'd like to call it. So hydrogen bonds are very strong as an intermolecular force, but keep in mind that they're still only 5 to 10% as strong as an intramolecular bond. So that would be like the bond between this hydrogen and this oxygen, whereas our hydrogen bond is shown by these dotted lines here, okay? And so in order to form a hydrogen bond, you need two things. You need a hydrogen bond donor and a hydrogen bond acceptor. And so again, your hydrogen bond donor should be an NH, an OH, or an FH. And a hydrogen bond acceptor will then be a lone pair. So if we were to draw the Lewis structure for these oxygen atoms and H2O, each of the oxygens would have two lone pairs. And so our hydrogen bond donor in this example is our hydrogen here on this water molecule, and then our hydrogen bond acceptor is this other molecule of water, okay? And together they form a hydrogen bond, right? Water is an exceptional case of hydrogen bonding because it is able to accept and donate two hydrogen bonds at a time, and that's really what gives water a lot of its special properties. So you can see that here, like we have two hydrogen bonds and two hydrogen bond donors, two hydrogen bond acceptors between these two molecules of water, okay? So that's it for our pre-lecture. If you have any questions, please email me or write them down, and you can ask them at the beginning of class. I hope you have a good day, and I will see you in class on Thursday.